Hi, welcome back to the restoration of this tube radio from the 1930s. Before we begin, I'd like to apologize for my voice because I'm recovering a bit from a cold, and although the worst part is over, I'm not feeling bad anymore. You can still hear it in my voice a bit, I guess. I sound a bit like you've stuffed a vuvuzela down my throat. But yeah, okay, so apologies for that. I think you're gonna have to live with it for this video. So, what are we gonna do here? Well, we're finally gonna get some action, hopefully. The idea of this video is to get the power supply going. And because when you're restoring a radio, or you're powering up an old radio, or any electronic equipment, yeah, first step is always getting a good power supply. So we're going to start with that first. But before we do that, there is something else I still need to do. I don't know if you remember it from the last video. I didn't put the volume control back. I still have that one over here. And we need to put that back first because it has the on-off switch attached to it. So without that, yeah, we won't have any power. So let's do this first. Now, I don't know if you remember, we talked about this volume control a couple of videos ago. It had an issue. It's a wire-bound volume control, and we had a break in the wire at somewhere, and I temporarily repaired it by just putting a bit of solder on this, but it's not ideal because it doesn't take solder very well, and I think it will obviously break again after a while. So let me see if it is still working like it should. So end to end we got 10K, 1.4. I think it's still okay. Yeah, I think it's still fine, because previously we had 20K instead of 10, and it jumped really suddenly from one place to the other. So there was a wire which was corroded and which was not giving great contact anymore, or it was still giving contact through the corrosion, which was causing the entire resistance to be 20K instead of 10K. So the pot seems to be fine. However, I don't know if this is a good way to restore this. I don't know how long this solder will last if you keep rubbing over it. So we're gonna do a proper job here. And the proper way to fix this is with conducting silver. So I bought some silver varnish, I believe this is. I don't know exactly how you call this. Yeah, silver conductive varnish. So the idea is that we very lightly apply this on the area where the break was, and then we leave this to dry. Don't know how long should this dry? Does it say? Silver conductive varnish adheres to very well to any glass material of circuit boards, ceramics, etc. For repair of circuit boards, windows, and very good conductive capacity. No, it doesn't say. Is there some shake before? Yeah, let dry. Okay, but apply multiple layers, let dry. Doesn't say how long it should dry. Anyway, we need to shake it first. And let me find my brush. So you can, I don't know if you can see this actually. Let me change my light thing position here. Maybe if I hold it like that, and if I focus. So the area of concern is this part over here. So what I'm gonna do is I'm gonna apply the silver here on the top part. It's the same place where I also applied the the solder. And that way there is also no, the contact here, the wiper doesn't rub across and doesn't rub off the silver, right? There is a bit in the cap here. I think we can use that. Yeah, we can use that. Cool. That should do, actually. So what we're doing now basically is we are bridging here the wires here in bit of this part of the wiper. So that means that yeah, we're taking this part of the wire out of circuit, this part of the potentiometer. So you will lower the overall end-to-end resistance, but it's better than nothing. So it should be okay. Man, this has a weird smell. So you could do the entire area here, that's also an option, but yeah, just the top is fine. If there is one part where the connections are bridged, it's okay. You can also use this to repair PCBs. If you have like very fine PCBs, or if you have circuit traces that need to be repaired, that's also a possibility, something that you can do with this. Okay, let's see what we got end to end now. See, still 10K, so I think it's okay. Yeah, see. Yeah, see, this is the area where we have the patch. And here you see that if you turn the wiper, that at a certain point, see, it stops increasing. And then it continues. That's because we are in this, here is the area where we are around 8.3, something like that, where we have this patch that we just made. And yeah, then obviously, see, it doesn't continue for a bit and then it moves on. So that's to be expected. I don't think the effect will be that big anyway, since it's a logarithmic pot. So it seems that it's also already dried, so that's good. It does feel a bit coarse now. You can feel when you're passing this area, but that's not bad, not too bad. It's better than throwing away the pot. Now the next part is, I don't know if you remember the video where I took this apart. This was totally covered with grease on the inside. And the grease is there for two reasons. One, to protect against corrosion, and two, to give the pot a bit of a heavier feel. So I picked up this grease. This is battery grease, and this is used for battery terminals in cars. And it's very cheap. I think I paid like €3.50 or something for this. The idea is that you put it on electrical connections, and it yeah, prevents oxidation. I think it's the correct grease to use in here as well. Just gonna see. Now, you'd ask yourself, how the hell will this work? Because if I put grease on there, it's gonna isolate the contacts, right? Well, yes and no. It will isolate the contacts indeed. And that's the point, because you don't want to get moisture reaching the contacts. But the place where the wiper is located, there is no space between the wire and the wiper, so it will push the grease away. Well, that's the idea. So let's see if it actually works. See if I can apply it like that. Yeah, that seems to work. A bit more, well, a lot more, I think. The reason why we had this issue with this potentiometer in the first place is oxidation, moisture, and probably on the place where the wiper was sitting and making contact with the potentiometer, with the wire itself. And it had probably been sitting in the same place for many, many years. And yeah, then the grease dries up. And then if you twist the button, if you twist the potentiometer, then at that place there is no grease anymore. And there is no fresh grease to fill in the gap. And probably that's where it was oxidized, I think. Now, I don't know how much to apply this. There was originally quite a lot in here. So let's already see if this is working. Yeah, that seems fine. It feels quite smooth as well. Feels very smooth, actually. That's nice. That has got a really nice feel. Let me just apply that more. Yeah. Anyway, if you apply a bit too much, it will just push it aside anyway. And after a number of years, it will be dried up anyway, and someone else will need to clean it out. So and also, don't forget to put grease here on the top area, even though there is the wiper will never come there. That part of the wire will still need to be protected from the moisture. So here, the top area is quite important as well. Okay. That's actually not too bad, I think. Do we still have contact? Yes, it does. Yeah, it does. It's working perfectly. Great. Okay, time to close this up. See, here we have the switch, and time to put the switch and the potentiometer back into the chassis. Alright, so the volume control is back in, and the on-off switch, including, it's all hooked up, so that should be fine. I also already did it earlier, but I forgot to mention, I hooked up the speaker as well, back to the chassis. I'll show you in a minute how everything is hooked up underneath. And I think we're almost good to go. I think it's important, though, that we have a look a bit at the schematic of the power supply just to explain you how it's working. Because it's quite a standard and common power supply system for this type of radios. So I think it's worth going into that a bit deeper. And since I am trying to dedicate all videos for dedicated parts of the circuit, so we're going to start on the power supply, it's also maybe interesting to do a bit more of a deeper dive into the circuit as well, and trying to explain how everything is working. Okay, so I am in the process of completely drawing the schematic of the entire radio, and I've not done much so far. I've only done the power supply section and the output tube. So I printed here only that part that I have already done. The reason is, well, I don't have an official schematic. The only schematic that I have is this one. I mentioned this earlier. This is a schematic which was drawn by I think John Koster, 2019. And this is a schematic for not this type of radio, but it's a very similar one. It has one tube less. My radio also has a tube in the RF section. So it is very similar, but as you see, there are quite a bit of differences, small differences, but I started marking them here on this schematic, and that soon started getting really, hard to read. So I just decided to start from scratch and basically draw the entire schematic myself. So let's just have a look what we got here. So we got our mains coming in here on this side. One side we have the switch, the other side we have the 2 amp fuse. Wait, let me get it because it's an interesting fuse. See, so it's this type of fuse that we have. See, it's a 2 amp, the 250 volt. And the fuse, although I drew it, I drew it correctly. The fuse is used as a voltage selector at the same time. So you have 3 positions on the back of the radio. And depending on how you plug the fuse, you also select the correct voltage. We can select between 110, 135. I think that's wrong. I think it should be 130. Yeah, it's 130. That's wrong. Let me just... And 220. So obviously for Belgium here we pick 220. That's it from the primary section. And on the secondary side we have 3 windings. Let's start here from the bottom. This is the filament winding for all tubes except the rectifier and for the dial lamp. And this is 2.5 volts. Then this winding here is the filament for the rectifier tube. So as you see, we have an 80 type 80 tube, which is a very common full wave rectifier from this period. We can have, I have printed out the data sheet here for the type 80 tube. We can have a look at that later. This winding over here is as I said, the cathode and heater for the rectifier tube. Because these tubes, they have the cathode is the heater as well. And as you see here on the data sheet for the tube, we have a filament voltage of 5 volts. So this winding here is 5 volts. Okay, so this winding here is the high voltage. So that's the voltage that we will rectify using the type 80 tube. And here we get the B+, which is then filtered once, then going through the field coil, filtered twice, and here we have the actual B+. Now, remember in my videos I always put a warning in the beginning, like watch out if this stuff can kill you when you're not careful and you don't know what you're doing. Well, this really applies to this winding over here because the setup, how it is done like this, is quite common in tube rectifiers. So you have a winding with a center tap to chassis. So we have on this side of the winding, we have 350 volts, and on this side, or 360, I don't know exactly, we will see how much comes out. And on this side, we have an equal value, also 360. And so that's the voltage that will get rectified, or the current that will get rectified. So that means that this winding over here, end to end, will be about 700 to 720 volts unloaded. So that's quite high. That's really, really high. So we really need to make sure that we take our precautions here when we are probing into this part of the circuit, because B pluses are already high. If you are thinking that like 250, 300 volts is high, here we are at 720 volts AC RMS. So that's really significant. So yeah, we really have to pay attention with this winding. Now, this capacitor over here, we'll come back to that one later. Just ignore it for the moment. Now, our tube here, if you look at the data sheet, so there are different ratings at which you can use this tube. For example, let's take number 1 here, and they say plate voltage per plate 350 volts, or rating number 2 400 volts. So this tube, yeah, can sustain, let's say, safely up to 400 volts. And then they say here, rating number 3, rating is permissible only with filter circuits having an input choke of at least 20 henries. And then you can go up to 550 volts per plate. So if I'm saying here like 350, 360 per plate, we are well within the maximum rating of 400 here. Anything else? So filament current is 2 amps at 5 volts. And if we are running it at 350 volts per plate, which is what I think we will be at, so as soon as we get load on the transformer, we can have a DC output current of maximum 125 milliamp. Now, what is also interesting is to see how much voltage this tube will drop. So let's look at this drawing over here, because see, here we have a condenser input to filter. We have the type 80 tube, and then we have, so each curve that you see here is related to a different voltage per plate. So let's say that we are here at 350 volts per plate, because that's more or less what we will be at. Then here on the x-axis you see the load. So depending if the load increases in milliamps, then your output voltage, the DC volt at the input of the filter, so that means the rectified voltage will drop as well. So let's say that we are at 100 milliamps here, more or less. Then with 350 volt RMS on the plate, we get also about 350 volt DC. So with a 120 milliamp load and 350 volts on each plate, we get, yeah, I don't know, a bit higher than 300 volts at the, let's see what this is, that is more, that's 320, yeah, that's 320, that's 330, let's say. So we drop about 30 volts. If the load is lower, then see, for an 80 milliamp load, we have a 360 volts DC at the input of the filter. So as you see, the voltage that you drop on the rectifier tube increases with the load in the system, which is as expected. We're going to test the tube that I got here with the radio in a minute. So here we have our rectified voltage. Then we go to our first filter capacitor. So that's a 15 microfarad capacitor. Then we go through the field coil, more about that later. And then again, we have a filter capacitor of 15 microfarad. Now, you might be tempted to increase these values because you think, maybe I want to reduce a bit the hum in the system. I'm just going to increase these values. Don't, really. There is a reason why they are so low. And that's because these tubes, they can't really handle the load of having big capacitors over here. So if you put a big one over here, then yeah, you will get quite a big of inrush current to charge the capacitor on startup of the tube, and that will damage your rectifier tube. So I believe that the 15 microfarad or 2 times 15 microfarad is more or less the maximum that you can put for an type 80 tube. Now I don't have this mentioned here in the in this spec sheet, but I recall to have read it somewhere online. I can't really say. So anyway, if you're working on these old tube radios, don't exceed these values too much. If you can't find a one-to-one replacement, don't go too high in terms of these values. It can damage your rectifier tube. Then we have here the 1.9K field coil. So we will drop quite a bit of voltage here over this coil, also depending on the current that we're pulling through the system. And then we've got our B+, and here we go to the amplifier circuit. So that's not for now. We're going to talk about that one later. Now, the tube that I got here with the radio. Let me get it. This is the tube that was with the radio. I cleaned it up, and it's an Adzam tube. That's a Belgian brand, so it's made in Belgium. That's quite nice. This is not. See this black part over here? That's not that it was burned or anything. That's simply a shield, or I think maybe it's the getter. I think it's the getter. Anyway, that's normal. What isn't normal though, it's the fact that it's wobbly. See? And I don't know if you can see this, but there is a crack here in the base. Can you see it over there? Yeah, there you can see it in the line of light. The base is slightly cracked. Now, I've been thinking about this, and I'm not going to do anything about that, because it's not that easy to fix. You can't just dump some superglue in there and hope that it'll fix it, because you have to run the risk of making things a lot worse. Because if you're going to dump some glue in there, then you're basically going to fix the tube against the base, which is what you want. The problem, however, is that your glue has a different rate of contracting and extracting with heat than the glass and the base, and in the end that can crack your glass, because if this glue that you put in there is not expanding as fast as the glass of the tube, then it will put some stress on the glass and it will crack your glass. So don't just dump a shitload of glue in there and hoping that it'll fix it. It's not a good idea. It's actually better to just leave it like it is. If it is like mine here, it's slightly loose. I just need to pay attention when putting the tube in and out and pulling it out that I don't break it. The good way to do is this, to remove the entire base and to fix it again with some new compound. And there is a lot of discussion online on what you should actually use to glue this back in. If I would need to do this, I would use tape, same type of glue that people use to glue in on stoves and on heaters and on things like that. To glue, you have these cords that run around stoves on the edges of a stove, and to glue these type of cord in, people are using glue. That's the glue that I would use for this, but I'm not sure. There's also no real consensus on this online, so I'm gonna avoid that, and I'm just gonna leave it alone. Now, this tube, I'm assuming that it's good, actually. I'm not talking about fixing the tube, but I'm assuming it's good. Let's put it on the tube tester, actually, and see what it says. Okay, so we've got the tube tester again here. First thing we're gonna do is put the tube in the correct socket, and that's this one over here, all the way in the corner. And I'm just gonna do it gently because of the cracked base. Okay, it's in. Now let's take all the settings. So this it's a full wave rectifier, so it means it has 2 diodes. So we're gonna need to test both diodes separately. Let me just put the settings in here for the first one. So we have settings here 3, 9, and all the others are 2. So 2 means ground. So that means basically, or unconnected. So this tube only has 4 pins, so that means only these 4 switches are relevant. All the other ones, they are not even connected to that socket, so they don't matter. So the settings for pin 1 is 3, that means filament. So these tubes typically, let me just pull it out anyway. See, you have 4 pins. You have 2 thick ones and 2 thin ones. The thicker ones are typically the filament. In this case, also the cathode, like I mentioned. And the pin numbering is typically starts from the one of the it's not focusing. Come on. Is this focused? Yeah, this is focused. No, it's not. But come on. Okay. So the pin numbering typically starts with one of the filament connections. So this is pin 1, and then it goes clockwise, pin 2, pin 3, and pin 4. So your filament in these type of tubes is typically always the first and the last pin. So in this case, pin 1 and pin 4. So here we have, it's quite simple. So you have two diodes, so one between these two pins and one between these two pins. So let's put it back. So pin 1 and pin 4, like I said, was the filament. So we have filament voltage here on pin 1, and then pin 4 is ground. And then pin 2 and pin 3 are the anodes of both diodes. So here we're now testing this diode. So here we have it set to 9, and 9 means a 5 kilo ohm resistor. So that's the way that this tube tester tests diodes, by putting a resistor in series. And the other one, pin 3, is simply connected to ground. So this one is, there is no connection on this one. So we're testing this diode. Like I said, filament voltage is 5 volts for these tubes. Plate voltage is 250. That's this guy. This is the range of my meter. Screens, we don't have screens, so we put these to 0. And I think that's more or less it. We should read 49 milliamps of plate current with this setting. So with 250 volts on the plate, we should have 49 milliamp. And let's see what we get. So the scale is 100 milliamps at the moment. I'm going to leave it at that, and because we need to find, we expect 49 milliamps. Let's see what we get. See, we have the tube heating up, and we're at 43? Yeah, 43. Okay. 43 divided by 49. That's 87%. So that's not bad, actually. That's still okay. Now let's test the other diode. So that's simply a matter of swapping these two switches. So we will put the plate of this diode to ground, and we will put the 5 kilo ohm resistor on this one. And we can just simply do the test again. And that one measures also 43. So that's good, actually. That's not bad. This tube is definitely still usable. And honestly, I think maybe it can even be an advantage for us, because these days we don't have 220 volts anymore on the mains here. It's most of the time closer to 240. So if we have a rectifier tube which is a bit weaker, that might actually help us. We will see what comes out of this tube. But definitely at 88% of original value, it's definitely still good. Now, there is only one component left that we still need to talk about here in the power supply, and that is this capacitor. Now, that's in Dutch we have a specific name for this type of capacitor, and we call it a Rattle Capacitor. I don't know if it also has a specific name in English, but it would translate to something like humming capacitor. So it's in fact an anti-hum capacitor, obviously. So the goal is to reduce the 50 Hz hum that is induced by the power supply into the audio signal. Now, how it actually works, it's a bit more complicated. It's just not simply filtering or anything. It's a bit more complicated. Let me try to explain. So imagine that this capacitor isn't there. And also imagine that we are receiving an AM signal via a very simple wire antenna. So not via a loop antenna or anything fancy, just a simple wire, okay? So there are a couple of things missing here in the drawing, obviously. We have everything related to the radio, so the detector stage, the IF stage, the mixer oscillator, the RF stage, that's all missing over here, because I haven't drawn it yet. But here we have the antenna, normally. And let's imagine that it's just a simple wire. So we're using a simple wire antenna. Let me just do it like this. Okay, now when you're receiving a signal, there is a current induced in this antenna, but I don't know if you have actually wondered how it actually works, because the current here in the antenna, it needs to go somewhere. It's just because on one side it's just a dead end. See, it's a wire, so it's a dead end at one side. The current is induced, but the electrons, they have to float somewhere, and they have to find their way somewhere. And they need to find their way to Earth. I'm not talking about chassis, ground, or anything here. No, really to the physical Earth. That's where they need to find their way to. So that's why I'm saying this doesn't apply to a loop antenna or anything fancy. This also doesn't apply to FM, to an FM dipole or things like that. No, just a simple AM wire. Now, where do we have Earth here on the radio? There is no Earth. I assume that we haven't grounded the chassis. So that means there is no path to Earth. Well, that's not strictly true, because the Earth here is in the street cabinet at the transformer. So your mains, let's say that this is the live and this is the neutral. Doesn't really matter, can be the other way around. Yeah, I don't have a lot of room here left on my drawing. So let's say that here we have the distinction. This is the transformer part in the street cabinet. Then at here, the neutral is connected to Earth. So let me just draw it like this, Earth. So this antenna current that is induced here in the wire needs to find its way all the way to Earth here. Now, how does it do that? You'd say, well, there is a transformer in between, so there is no way that it can flow to Earth, right? Well, that's not strictly true, because if you're using a transformer which doesn't have an electrostatic field inside to completely shield the primary and the secondary winding, like this one, it doesn't have an electrostatic field inside, and most normal transformers don't, then you have here a sort of, how should I call it in English? A parasitic capacitance or something like that. Imaginary capacitance between the secondary and the primary winding. So let me draw it like this. This is not a physical capacitor, it's just a imaginary capacitance between the two windings. Right? So like this, there is a path to Earth for this antenna current, right? Now this goes into the entire radio section. Let me just draw it like this. This is the RF, the mixer oscillator, the detector, the IF, whatever. Let me just draw it like this. Doesn't really matter. So the antenna current flows like this, comes in over the B+, and we're still imagining that we don't have grounded the chassis, and this capacitor is not in place. So what is the path it will follow? It's going like this, coming in like this, the antenna current. So we're talking here about an extremely tiny current, right? Because it's what is induced in the antenna. Then it needs to find its way to here. Well, it's doing this. It's going through the detector tube like that, following this path via this is going to mess up my marker, but it's following this path like that, and that's how it gets to Earth. Now, the problem with this is that it passes here through the detector, because the detector is fully busy trying to rectify the 50 Hertz AC mains voltage. And in doing so, the resistance of the detector here is changing quite often, because when it's conducting, it has a low resistance, and in the period of the sine wave where it's not conducting, it has a very high resistance. So this means that your tiny little antenna current will get modulated with the 50 Hertz tone of the, with the 50 Hertz signal of the AC, and you will hear that as a buzz in the audio, because you will simply modulate the 50 Hertz onto your the antenna, the signal that you received on the antenna. Now, how do we avoid this? Well, we could ground the chassis, right? If we simply ground the chassis, if we use a 3-wire plug and we pull an earth wire or a ground wire here to chassis ground, then we're basically done. So, but let's say we don't do that then, and we put in this capacitor here in the circuit. Now the current will flow like this. It will find a lower resistance path than here through the rectifier tube. It will go like this. It will go to chassis. And then once it is here on chassis, I don't have a direct link, but here we also have a chassis connection, right? So it comes out here, goes through this capacitor, and then it follows the same direction here to earth. And as you see, we have bypassed the rectifier tube. And this should significantly reduce the hum that would otherwise be induced. Now, like I said, we can also simply just ground the chassis, because then the antenna current will flow like this. It will bypass the entire power supply section and will here straight directly to earth. Now, this capacitor, it only makes sense, or it only has a function, like I said, if you use a wire antenna and if you haven't grounded the chassis. I hope that's clear. This is the way of working. A lot of people who know that this is an anti-hum capacitor, but they don't know exactly why it is or how it works. Now, this is the explanation, and I hope that makes a bit of sense. Now, let's have a look at the chassis itself and see how far I am at rebuilding the power supply. Okay, so what are the things that I've done here? I put back the volume control with the on-off switch. I wired everything, I hope, correctly. I put in a temporary lead. This is only temporary. Once the restoration of the radio is finished, I will put in a much nicer and more period correct lead that looks a bit more original with a cloth covering and etc. This is only temporary. So one side is going to the on-off switch. The other side here is going to the voltage selector. Now, if you think, what is this kind of abomination with this fuse here? Bear with me for a second. Normally, like I explained on the schematic whoa, this is blown out. See over here, where you have the voltage selector, where you use the fuse to select the voltage. Yeah, it's this fuse that you would normally use, and you need to plug it in here in the correct position. Now, the problem is that this is such a vintage fuse, I don't have any spares, and I don't want to blow it. So I really want to first completely restore the radio, make sure that everything is working correctly before I put in this fuse, because I only have one like this, and I don't want to blow it. So that's why I soldered here temporarily a 2-amp fuse here in the correct position. Then next, as you see, I disconnected the 2 filter cans, the 2 original filter capacitors, and I put these ones in circuit instead. So these are exactly the same specs, but a lot smaller because they are modern. These are 15 microfarad, 450 volts. What else? Oh yeah, I also connected the speaker. So these are the wires here coming in of the field coil. So one is going to this capacitor and one is going to that capacitor. And you see here on the schematic, this, oh, so blown out. You see here the field coil is basically between the two, positive sides of both capacitors. The third wire coming from the speaker, that's the one of the connections of the output transformer, and that one is going here to the output tube, but that's not, I already put it in place, but we won't use it yet because I don't have any of these tubes in circuit. This box over here, that one is containing two capacitors, and one of the two is the anti-hum capacitor that we were talking about. In my explanation that I just did, I made a slight mistake. I now notice that I put here 1 microfarad. It should be 0.1 microfarad. So 100 nanofarad is the value of this capacitor, which is actually slightly high for an anti-hum capacitor. You would expect it to be a bit smaller, but okay. So this one contains two capacitors, and they are both rated at 1500 volt. One of the two is the 100 nanofarad anti-hum capacitor. The other one is the 500 nanofarad cathode bypass capacitor for the 2A5. Now, there is absolutely no reason why this would need to be a 1500 volt rated capacitor, because it definitely doesn't get this amount of voltage. This one I can understand because it has 360 volt RMS AC on top of it, but this one, absolutely no need. I think they just had these boxes which contained two capacitors and they simply used one which was unused as the cathode bypass. Now, how is it wired? Let me tilt this up a bit. There are three connections. The center one is the common ground for both capacitors in this box. This pin is the anti-hum capacitor, so the 100 nanofarad, and this pin over here, it's the for the cathode bypass, so the 500 nanofarad. And the capacitors in this box are also paper capacitors, so they definitely need to be replaced anyway, and also need to clean it up still a bit, because I haven't done that yet. Now I do have a replacement for the anti-hum capacitor, and that's this guy. That's a 100 nanofarad rated at 1600 volt. Okay, here we go. I think I have everything hooked up. I have the radio connected to the dim bulb, and I only have one bulb of 15 watt in series. I also don't have any tubes in there at the moment, so it's just the transformer. So we shouldn't have any B plus yet or anything. So it also means I don't just really need to change any of the capacitors at the moment, because they are not in circuit at all. We don't have the rectifier tube at the moment. And I'm measuring here across this hum capacitor. So we should measure something like 350, 360 volts. Again, it's unloaded, so there is no load at all. So what I'm going to do is simply measure all the windings here. And let's start with this one. Now, I have the radio turned on. The power switch is on. Yeah, this is off. That's on. Whew. This is kind of exciting. Really exciting, actually. This is the first time in probably multiple decades that there will be power going onto these components. So, one small remark. I also have a dial lamp here. So this is a 2.5 volt bulb that I had to buy specifically because I don't have any 2.5 volt bulbs. So watch out for that one too. Let's see what we get. Nothing. 286. That's not that great. I also don't see anything on the dial bulb. Maybe that's not making good contact. Could be that maybe it's not going deep enough in the socket here. We will have to check that later. But 280, that seems quite low. Let me try that again. But okay, yeah, we are... Oh yeah, I'm only supplying 167 volt here because of the 15 watt bulb, and the bulb is glowing. Let me show you. See, the bulb is glowing a bit. Ah, the dial lamp has come on. Huh. I guess it didn't make good contact. Awesome. And we have 282 volts. Okay, let me turn that off again. Because every time I'm going to switch here, I'm going to turn off the power just to be safe. Let me check here the filament. So these connections should be the filament voltage. Let's see. We have 2.15 volts, again at 167, 68 volt input. That seems fine. Let's check the filament of the rectifier tube. So that is, just for reference, this winding over here should be 5 volt. I think I have everything turned off, huh? Yeah, right. Okay. I think it should be that one over there. Turn it on. 4.3, that also seems in the good ballpark. Let me switch here to a bigger bulb. What is this? This is 25 watts. Oh, that's 6 volt already. That's too much. Ah yeah, because we're now getting in 235 volts. So the 15 watt bulb is not enough. The 25 watt bulb is already too much. So let's go back to the 50. Now I think, yeah, I think we're okay. I think we're okay. Let me just for curiosity here also measure completely across this winding. Oh. So this winding, measure completely across it. There we should have double. So now more or less 500. And when it's fully in use, we should have about 700. 561 already. So yeah, everything seems to be in working order. Oh, I forgot to adjust the lighting here. My apologies for that. I think we might try to put in the rectifier tube. So the rectifier tube is in. I checked if there aren't any capacitors that need to be swapped before we do this, but I don't think so. I didn't notice any capacitors that should be changed. The only thing is this guy over here. That's the one here going to this tone control switch. If I leave the switch in the open position like this, that should also not have a path to ground. So that seems fine. This one should show the B+. This one is across that hum capacitor. So that one is showing the voltage at one of the plates of the rectifier. So this is the AC voltage going in one of the diodes. This is the B+ coming out of the rectifier. I think I have everything hooked up. Now this over here, that's the B+ basically. So see, it is going around here, so it's quite accessible. As you see, it's also available directly on this bus. Maybe that's not a bad idea to just take it from that bus. Just give me a sec. Yeah, as you see, the let's say safety regulations weren't that strict in 1935. So if I just do this and then take it over here, I should also have the B+. Okay, let's see what we get. I again have the 15 watt bulb here on the dim bulb tester. That will not be nearly enough. But let's see if it is enough to get the rectifier going. Okay, yeah, this is quite exciting. Let's see what we get here. That's climbing, but really low. Let's see, we have the rectifier is going. It's working. 70 volt. We had 150, only 150 volt going in. And we have DC 130 volt coming out. Now I don't know if this is measuring RMS, true RMS. I think it is, because see, we have 153, 150 coming out here and still climbing. And the bulb is actually very dim now because we have the extra load of the rectifier, but this seems quite okay. Let me just turn it off again for a second. And let the B plus drop again, because the capacitors here are now discharging. Maybe we can try again, but with a 25 watt bulb. I'm now have only 150 volt going in here. We've got, what, let's say 260. Yeah, let's say 260 here on the plate and 340 coming out of the rectifier. So let's see if that is more or less what we expect. So without load, so we really have to check here all the way on the left of the schematic or of the drawing. 250, I said, right? 250 on the plate, and if you continue there, then you see that it will end up above 320. So if you would continue that line imaginary, you would end up somewhere right there, and indeed that's 340. So that seems to be correct. So I believe that we have the power supply working, and I'm actually really tempted to simply continue and try to get the amplifier working as well. But that means that we'll have to go to the tube, the 2A5, and I'll have to start checking which capacitors that we need to replace over here in the amplifier. Make sure that we don't forget any of those, and also checking the resistors that we have here. The setup with this tube is very simple. So let me just have a look at that, and maybe we can even try to start up the amplifier still in this video.